So, welcome back. We are coming to an end of this chapter on electromagnetic waves shortly, and then we go to the next chapter, and that is ray optics. Well, electromagnetic waves, as you know, they are waves with a very wide spectrum of frequency and wavelength. The frequency varies from 10 to the power of 1 to 10 to the power of 23 hertz. And the lambda, corresponding lambda value goes from 10 to the power of 7 to 10 to the power of minus 14 meters. And of course, their optimum speed is in vacuum, something called nothing. Okay, so in free space, and that the speed is that of the speed of light, which is experimentally determined from before. It's matching with that value. It's basically 2.9999 in this that, and which is approximated to 3 into 10 to the power of 8. Okay, neither I am interested in telling those numbers, nor you should care. 3 into 10 to the power of 8. So as the name suggests, the electromagnetic waves, they must be some waves in the electric field and in the magnetic field. And interestingly, these fields should be perpendicular to each other, so that E dot B or B dot E must be equal to 0. Remember the vector definition of vectors A dot B, like that. And both of them, E and B, are normal to the direction of propagation. So there are all three directions which are possible. Direction X, for example, you take for the electric field propagation, direction Y for the magnetic field propagation direction. Okay, they are together, and then the direction Z or Z is the direction of propagation, which is evident from this. So the electric field and the magnetic field, they are present together, and they propagate or travel like traveling waves we have discussed before. Will not discuss much about them, but we have Ex, the electric field vector in the x direction, is equal to E naught, its maximum value, when this turns out to be equal to 1 sine of kz minus omega t. So this is a sinusoidal wave. We have taken the simplest of the waves as the representative wave, and By in the y direction is B naught sine of kz minus omega t. This is in the positive z direction. If it were in the negative z direction, then it will be kz plus omega t, kz plus omega t here. Wait. In this argument of the sign, in the phase of sign, we don't have any expression of x or any expression of y. So let's see that this k over here is 2 pi upon lambda, is called the wave number, lambda is the wavelength, and omega is equal to 2 pi upon capital T is the angular frequency or the angular velocity, however you want to call it. T is equal to 1 upon nu, the time period. Okay. So these two, they propagate in the z direction. Okay, with time. Now let's see, and let us talk about the production. So the production is attached to the motion of charges. are charges. But how about stationary charges? No propagation. Steady currents which give constant electric field, di dt is equal to 0 in steady current because I does not change with time. So the answer is, sorry, there will not be any production of electromagnetic waves. What we learned due to the Maxwell's equations, that accelerated charges. How about the accelerated charges? The answer is yes. Because accelerated charges give rise to magnetic fields, those which change with time, and we'll see that the ddt, this gives rise to dvdt, and dvdt gives rise to ddt, and that to this and this to this and this to this and so on. We just write and see, and that means and so on. This process is continuing. Well, if there is an energy density associated with the electric field, half epsilon naught E square, okay, this gives rise to half B square upon mu naught. Okay, this is the energy density of the magnetic field and that of the electric field, and so on and so on. Okay, so there is another thing, that there has to be an oscillator which accelerates the charges and its frequency will be equal to the wave frequency. Okay, or the wave frequency will be equivalent to the frequency of the oscillator, electronic oscillator, which is giving rise to the electromagnetic waves. Now, the energy associated with the propagating or traveling wave comes from the source. And what is the source? The source is accelerated charge. And then it appears that if we are able to measure the electric field or the magnetic field, okay, as a function of time, and from the wave, that is, if the detection is there, production and detection, they are two processes. So it appears that with our sense that we can see some colors of light which are emitted out. The yellow color belongs to a frequency of 6 into 10 to the power 14 Hertz. This is a very large frequency. Whereas I have said that it can go to 10 to the power 23 Hertz. So naturally, there is no means that we can produce the things and then verify them, and that is, this kind of an equations are verified. So because even today the best electronic oscillators that are available with all the progress in electronics, that is only to the order of 10 to the power of 11 Hertz, which is very low as compared to this, even for the yellow frequency. Okay, it's in the range of about 6,000 nanometers as far as the wavelength is concerned. So for verification, we had to go for the early production of electromagnetic waves and their detection of electromagnetic waves, which today we know as the radio waves, and that was done by none other than the great of that time, and that was Heinrich Hertz, who died at a very young age of 37. And this was put to use by Marconi, who used it for communication, okay, for certain kilometers in the continent, on the continent, okay, in Europe. But Jagdish Chandra Bose, the learned physicist of that time in Calcutta, he produced these waves and much shorter wavelength, very effective in Calcutta at that time, the capital of India. So, and this is how these waves were later on used for communication purposes. Anything has got an amplitude, a frequency and a phase. Any wave has got three characteristics: the amplitude, its frequency and its. And if we have information, say even sinusoidal information, how to communicate from one place to another place, and that part we take up the end of our this thing when we are talking about communication. So any one of them can be modulated according to the signal which we want to communicate. And when, so this is called, if we vary A, amplitude modulation. If we vary nu or frequency, then there is frequency modulation. Okay, and these days you have many Ganas on the FM, it's called FM. And then phase modulation. So these are some of the modulation systems which we use in the analog communication systems. But these are the days of digital communication. So we combine them together and we convert things in digital things which are not as smooth as the analog things. But anyway, we are able to control those things and have the communication systems. Okay, so I talk more about it. So to prolong the discussion, I have just tried to give you a schematic this thing of the variation of the electric field and the magnetic field. Electric field varies in the XZ plane and the magnetic field in the YZ plane. This is shown with the red ones, and I've shown the directions which become reversed and then again reversed like this. The same thing is there, you can have a look at it. From here to here or from here to here, it is one single wavelength and of course one time period. So in keeping with what we've learned before in the propagation of traveling waves, simple harmonic waves, we say that the speed of propagation of the waves, the traveling waves, is given by omega divided by k. So omega is 2 pi upon capital T and this 2 pi upon lambda, and this becomes lambda upon T is equal to C. Okay. So I get a famous relation that omega is equal to k into the speed c, or the one which we also found in the case of sound waves, etc., that c is equal to nu lambda. Often nowadays we used to call it, this is n lambda, because these symbols were not available in the types in the books. So we used to use the Roman symbols, not the Greek symbols. So c was taken as equal to n lambda. Of course, they have their own units, and the unit of c is meter per second. Also recall that we found that c was equal to 1 upon mu naught epsilon naught. And then I can write the velocity in any medium, this is equal to mu into epsilon, where mu and epsilon are the permeability and permittivity, in the media under consideration. Okay. Of course, we learn in due course of time that the ratio of the two is also given as the refractive index, but that we'll talk about in the next two chapters. Now, I just introduced to you the electromagnetic spectrum, which I said it ranges from 10 to 10 to the power of 23 hertz and 10 to the power of 7 to 10 to the power of minus 14 meters. Okay. If we go in the order of increasing frequency or decreasing wavelength, then we have the set in that order: long radio, amplitude modulation radio, TV and FM radio, and short radio waves. TV is also a kind of radio. Okay. So next we go, after this we go to microwaves, which you know is used to excite the water molecules in our food, and this is also used for many other purposes, military purposes, etc., etc. After the microwaves we come to IR, infrared, visible and ultraviolet, where this is the one which we can sense the best. We can sense the infrared also, we can sense the ultraviolet also, because it has its own effects. Then come up the very short wavelength and very high frequency waves, which we couldn't know what is the source of it and how they are obtained, and those days a beautiful name was given to that: X-rays. Okay. So all these things are because of the electronic things associated with atomic structure. Okay. But then we have gamma rays, and the gamma rays, they come out of the nucleus, because out of the nucleus there is a transformation. Then we have, if you remember in earlier classes, alpha, beta and gamma. Okay. But alpha and beta are particles. Alpha is doubly ionized helium, beta is electrons, and gamma is EM radiations. Okay. So these gamma rays are having a very high energy associated with them. As you know that the energy is also equal to h nu. Okay, we'll talk about that later on. But sometimes the hard X-rays and soft gamma rays, they overlap each other. I'm leaving you here. I understand that all books, they are describing these things in much details, and it is not my purpose to give you those details, how they are produced and how they are detected and what purpose they are being used, etc., etc. This you can, I refer you who are good boys and girls, you can search for yourself and learn these things, because they are worth learning. Okay, at least the order. Okay, so with that, it's an end to the book 1, which is normally taken in one of the very important and big boards in India, CBSE board. Okay, and catered by NCRT books. So it is part 1 of the book, which is over, finished, and now we go with part 2 of the 12th class and start with the ray optics, talk about reflection, refraction, mirrors, lenses, prisms, and then certain instruments, telescopes, microscopes, eye as an instrument, etc. It's very interesting. So wait for that, and I long to see you in those lectures also. Okay, so it has been my pleasure. I have enjoyed talking to you. Hopefully you also take these lessons in their stride. And if there are any things that you have to, you don't understand how the things are related, my lectures are open for discussion. So it's not only for appreciation. Fortunately, so far I have not been called names by anybody. Okay, but even if you call names, I don't mind. I will just take that you have not been able to understand that. So actually, the very philosophy is that everybody should be able to ask questions. This is how a child grows, and it is our purpose, after I have grown from childhood to 73 years of age, to answer or ask my colleagues, my friends, my old students to answer that for you, so that I can communicate without modulation, okay, to you. So thank you very much.